So welcome. Everyone enjoying reInvent? Having fun? Cool. I'm going to do a real quick show of hands. I'm curious. It's been a long week for me already. How many people are here for their first reInvent? Wow. Okay. Second reInvent? Keep their hands up. Second reInvent. Third reInvent? Any third? Anyone remember the pub crawl last night? No, I didn't go out. See, I did a talk. So thank you really an awful lot for coming today. My name is Dougal Ballantyne. I'm an HPC solutions architect for Amazon Web Services. HPC is high-performance computing. It's really hard to do high-performance computing without touching block storage. So I'm really excited to be talking about EBS today. So what we're going to cover in this session, it's the EBS service deep dive, is an overview of EBS. What is EBS? Okay, we have volumes, snapshots. We're going to talk an awful lot about performance. How do we achieve performance in EBS? What kind of performance can you expect from EBS? Big shout out to Werner. I had to update my slide deck. I will be covering larger and faster volumes today. We're also going to be covering encryption as well and some of the changes we announced yesterday in encryption. So let's jump into the Amazon EBS overview. To start out with, for most people inside AWS, most builders, it's truly get in and go. You provision an EC2 instance, you attach an EBS volume, you put an application or data on top of it. We introduce GP2 volumes or general purpose SSDs, so they just fly without doing anything, and you're off, you're good to go. But what I want to impart with you today, the time I want to take today is to explain to you if you do need to think about building, if you do need to think about architecting an application where performance matters, consistency matters, or you need to achieve a particular goal within your architecture, that you know how to choose, how to size, and how to operate EBS effectively. So, a normal hard drive. A normal hard drive. Okay, so I'm assuming everybody in this room is committed to memory, some of the numbers for the drives they've had to build over the years, the spinning rotation, 7,200 RPM, the number of IOPS it takes to build out an array for a database, or what size do I get with RAID 6 and the parity overhead. And those are really great numbers to commit to memory. I unfortunately have loads of them stuck in my head still. And the reality is a really well-architected application, one that makes a difference for your business, is one that has been designed on top of a solid, stable storage system. And so knowing this and getting it right is really important, has been really important for a long time. Fortunately, our EBS team and Amazon know an awful lot about disks, an awful lot about storage subsystems, and they've pulled all of that together and turned it into a service so that you can easily and effectively launch a storage system with a one API call and a couple of parameters that delivers a significant amount of performance and capability without having to think about how did they get the IOPS in there, how did they get the sizes in there, and how do they make it operate at that level of availability or durability. That being said, EBS is by no means a hard drive. EBS is a service. And because it's a service, it's built out of multiple components. It means they can build different availability and durability goals into those components to deliver it in a completely different fashion than a JBOD attached to the back of your server or a disk that you pick up and plug into a system. So what is EBS? It's persistent network block storage. That means it's not part of EC2. It's actually something you attach to EC2. It operates independently from EC2. If your EC2 instance dies, if your EC2 instance is terminated or you intentionally get rid of it, EBS is still there. EBS is completely independent from EC2. You can attach it to an EC2 instance within the same availability zone within moments. So you can do things like scale up auto-scaling, quickly attach EBS volumes with new data sets, and they're immediately there. It supports something called supports something called snapshots. And snapshots are a persistent copy of your data in the S3 durable data store. So this enables you to increase the durability of EBS well beyond any of the replication that's already done on the back end for EBS. The data is replicated within the availability zone. This enables a significantly higher annual failure rate than you're going to see with any kind of hard drive that you would attach. And I'm going to reiterate this. EBS is a service, and because it's a service, it means that we're delivering a totally different way of thinking about it. So availability for EBS is engineered for 5 nines of availability. If we take a look back into the service, we're actually exceeding that in the last 12 months. We operate today at 9.9, 9.99, that's the 5 nines, 5, sometimes 6. So we're far exceeding the design goal. And that means you can truly build on top of EBS and rely upon it being there for you. So before I get too deep into the presentation, before we go too far into understanding this, I want to make sure we have a few definitions outlined, okay? These are kind of important because these are topics we refer to both in the EBS service, the way you provision volumes, the way you manage volumes, the way you observe volumes performing, okay? So IOPS, input-output operations per second. This is the number. You can typically dial this in or it's part of a burst capability. Our throughput, how fast can the volume go? The latency, how long is it taking to get the backs, the reads and writes, the bytes backwards and forwards from EBS? How big are the volumes? And as we heard this morning, they can go a lot bigger than they previously did. And then this one's kind of interesting. We'll dig into it as we go further. What is the block size you're using, or what is the block size the application's using, and what does that mean to EBS and how it operates? So let's dive actually into what EBS volumes are. So we have 3 types of volumes today. And if anyone knows, we launched EBS Standard in 2008. So we've already iterated. We've added 2 more volumes. That's the great thing about a service. We can keep adding things to it and improve the service without you having to re-architect applications from the ground up. We have general purpose SSD. So general purpose SSD was introduced this year, if my memory serves me correct. And that brings to us SSD-backed volumes for all use cases that we can find today. Okay, you can start out with your boot volumes. You can do databases on it. You can use it for a file server. And then that's really cool. I mean, there's some really cool stuff, and I'm going to spend a lot of time talking about that. Provisioned IOPS. Provisioned IOPS was the first SSD-backed volume type. It's designed to target really, really high-performance database-type workloads. When I talk about database-type loads, the type of workload where if you had a single stall when you were doing a select or an update in the database and that made a difference to your application, provisioned IOPS is the type of volumes you're looking for. And then magnetic, and I'll spend a little bit more time as we go through talking about magnetic, because magnetic's still cool and has a really cool purpose inside the platform. Takeaway here, the tip I want to leave you with as we start, always use SSD-backed volumes if you're interested in performance. If you're truly concerned about performance, the PIOPS platform is going to be the one you're looking for. When I talk about performance, it's performance consistency. There's a lot of performance in GP2. It's the level of consistency it will deliver. So all of the SSD volumes have these characteristics. So the IOPS are now measured in 256 kilobytes. So if anyone has been using PIOPS since last year, those were 16K IOPS. That meant if you sent 64K block writes down to the PIOPS volume, we chopped it up into 4, and we charged you 4 IOPS out of the amount of IOPS that were provisioned in that volume. Today, it's 256 kilobytes. That's really important. That means we can now do streaming I/O through these volumes at a significantly higher rate. We've also done some magic when we launched the service and started to do a much more aggressive I/O merging. What that means is, even if the block size in your block device is set at 64 kilobytes and you happen to send 2 blocks which are sequential, and we notice that, we'll do our best to make that up for you and recover that so it only turns into 1 IOP. So it's going to help you. Even on PIOPS, we'll do that. Single-digit millisecond latency. Now, what I mean there is it's designed for that. You have to be aware of how to achieve that, and we're going to spend time talking about that, but you can achieve single-digit millisecond latency with reads and writes to EBS all the time if you architect correctly. And I said already, availability, 5 nines of availability, I think in storage is pretty phenomenal, so it's pretty cool. I didn't mention this, our throughput. So our throughput has increased substantially. Previously, throughput was 64 megabytes a second. And I noticed lots of pens and papers and photographs. All of our slides are available after reInvent. Unfortunately, this is recorded. That'll come back to haunt me. So you can get hold of all the slides in about a day or two's time, and you can take all the numbers back down again, so you don't need to worry about writing it all down. Throughput's increased substantially on the volumes, and it's gone even further with larger and faster we'll dig into, but 128 megabytes a second. So, general purpose SSD volumes. Spend a little bit more time digging into actually what they do. So it's the new default volume type for Amazon EBS. When we say that, that's things like when you open up the console, it's going to pop up a little warning to you saying, you're not using GP2. Would you like to continue using GP2 for this next launch? Because we really think it's the right volume for almost all of the workloads that you're going to have in front of you. Every volume supports 3,000 IOPS up in a burst configuration. And I'm going to spend a lot of time talking about that for you to understand. A storage volume that has burst, I think, is unique. It truly is unique. Typically, a hard drive or an SSD has a very set level of performance characteristics, a certain block size. This goes up and down. It's really cool. We can do 3 IOPS per gigabyte baseline performance, and I'll dig into that in a little bit more. And it's designed for 99% consistency in performance. So what that means is 99% of the time you will achieve the IOPS that you're looking for from this volume. So I'm going to spend quite a bit of time here because I think this topic is really important, understanding how our I/O burst bucket works. So every single GP2 volume created today starts out with an I/O credit bucket of 5.4 million IOPS. And you can spend those IOPS at up to 3,000 IOPS per second. And it's a bit confusing, IOPS per second, but it's the way the credit bucket works, okay? The baseline performance, or the input rate into that bucket, is going to be 3 IOPS per gigabyte. So if we had a 100 gigabyte volume, it's going to be accumulating at 300 IOPS per second. So there's always going to be stuff going back into that bucket. And you can use that bucket as long as you want for the IOPS until there's no credits left, and then you'll always get the baseline performance. So if it was provisioned at 100 gigabytes, it's always going to deliver 300 IOPS at 99% performance consistency. I wanted to give you an idea about burst versus reality. Burst sounds like something that just, like a firework, burst. That's not what EBS is doing here. What EBS is doing is giving you a really long period of sustained performance. So this graph illustrates how long it would take to drain the bucket if you run it flat out 3,000 IOPS all the time against size. So how long it takes versus size. I'm going to pick one here in the middle. A 500 gigabyte volume will take 60 minutes flat out. You have to be running 3,000 IOPS, no change, no dipping below, and it will take 60 minutes to empty that bucket. It doesn't happen. We have a really tiny percentage, 0.3% of all GP2 volumes created today have exhausted their I/O bucket. It's just not happening. So I don't want you to think about this as burst when you go away from this. I want to think about it as something that's going to deliver a really elevated level of performance that you can actually use in a lot of different ways. So what does GP2 mean today? Like, what does it mean to your application when you're architecting with it? So I've got a couple examples here. The first one is the typical boot volume. So a Windows boot volume is 30 gigabytes on average. It always comes with an I/O credit, 5.4 million IOPS, and it could burst for 30 minutes at that rate. So you could be running flat out for 30 minutes. It's not likely you're going to do that, to be candid, unless you have some architecture that does that. But you're not going to be doing that. To boot a Windows instance doesn't take 30 minutes. It takes longer than Linux, but it doesn't take 30 minutes. So 90 credits a second it's going to be accumulating, so it's always adding in the background. We sat down and did some testing, and we did compare Linux to Windows. And what you can see here is by using GP2 volumes just for the boot volume, and when I say this, we didn't re-architect the AMIs, we didn't change the application. All we said when we launched the instance was don't use Magnetic, which it was previously using, use GP2. And we see a 40% reduction in boot times. And that's there today. You should just be able to do that by launching an instance and choosing the right volume. If I take a look at our, move next slide. If we take a look at databases of workload, if you're using PIOPS today because Magnetic wasn't able to deliver the performance you needed, so you moved over to using PIOPS, which I think is honestly the right direction to go, and you had a 1 terabyte PIOPS volume doing 4,000 IOPS, the cost of that would be $526.40 a month. It's going to deliver exactly what it says on the box. You could grab one GP2 volume today. It'll give you 3,000 IOPS, so we're going to drop down in IOPS a little bit, do it for $102. But we could also take 2 500 gigabyte volumes. I know the dreaded striping, but there's some nuances here. Put them together, and for the same price, exactly the same price, you'll get a peak of 6,000. And it'll be sustained at 3,000. So this is a really cool way of thinking about it. You can do some really cool stuff with that. The throughput on this volume, 256 gigabytes a second. That's an awfully big amount of performance at that price. So how do you think about sizing GP2 volumes? So for almost everything, if it's not specifically tied to a baseline provisioned IOPS, it's going to be the size. Just pick the size of volume you need, and you'll be able to provision it. I'll talk a little bit more at the end about what larger and faster means for that. If you're doing database applications, and when I talk about database applications, the ones that we think fit best into GP2 are the databases that don't require the highest level of consistency. And the highest level of consistency, like I mentioned, are the ones that just cannot tolerate any I/O stall or any change in performance. So we see a lot of databases performing really well on top of GP2 without having to increase their cost and architecture for PIOPS. Typically what you're going to do is work out what your baseline is. So if you need 300 IOPS, you're going to take that, divide by 3. It's going to be a 100 gigabyte volume that you need to put underneath there. You may be able to go a little bit smaller if you're comfortable with the burst capability. Like we discussed, it's going to burst for a long time, but it's pretty easy to size those. EBS provisioned IOPS or PIOPS or PIOPS, depending how you want to go through it, is designed truly for the high end of performance. Internally, we would talk about these as tier 1 databases, the critical timeline database that everything needs to operate perfectly. The big difference between PIOPS and GP2 for me is the fact that you can provision a significantly smaller volume, 134 gigabytes, and drive all of the IOPS through the volume. So you're not over-provisioning capacity to get IOPS. They have a much larger ratio of IOPS to gigabytes. And again, the performance consistency is an extra 9, so 3 nines of performance consistency. EBS magnetic, or standard as we used to call it. EBS magnetic should really be seen as nearline storage within the architecture today. If you've got cold workloads, you need a file system that must be there no matter what, but you rarely access it. That's where EBS magnetic is going to come into play. If you have an application that must save something onto block store, but you cannot architect it to be redundant across ephemeral or something like that, EBS magnetic is going to be the solution for that. The cool thing about EBS, and we'll talk about a little more, is snapshots. So you could easily get off EBS magnetic if you change the architecture of your application by taking a snapshot and relaunching the volume on top of GP2, and you'll immediately have all the benefits of GP2 with all the data that was on the volume. So it's not a design decision that you live with magnetic. It's based on the workload. What are you doing with that workload? There we go. A little bit of a cheat sheet. These things are just awful, to be honest. But it's really important that we put all the numbers up there so someone can get a picture and take it home with them. So this is as much as we can put up on one slide about all of the performance. I think the big takeaways here is the latency is consistent across all of our SSD volumes. The max I/O per node is the same. It's really about how many volumes you add into that instance. And then classifying them. The PIOPS is really truly focused around high-performance databases. So why did we make GP2 the default? Why is GP2 kind of in your face on the console? Why am I taking so much time to explain it? Well, we've been able to deliver a really high baseline of performance, and we want to make sure you get access to that. We did a lot of work to make GP2 possible, and we want to make sure you're using it. It's a really great piece of technology. The burst capability fundamentally changes how small volumes operate. And so typically people had a Windows instance in an autoscaling group, and they were actually architecting solutions to deal with the boot time of the Windows instance so that when it autoscaled, they would have enough in that fleet while the Windows one was booting up. GP2 is there to fix that. It's there to help Windows instances boot faster, so you should be using it. We changed the pricing. It's a single price, 10 cents per gigabyte per month. It should be very simple for you to architect out what it's going to cost to run a solution based on the storage it requires. And from our side and your side, it's just very attractive. All of the numbers line up. You got a lot of IOPS for a really good price and a really good density. So big takeaway here, please, would be always use general purpose SSD for boot volumes. If you're not doing it today, and the one thing I impart upon you is that, please do that. It makes such a huge difference to your applications. How do you get onto GP2? So if you're on magnetic today, or if you're on provisioned IOPS, how do I get over to GP2? You keep telling me that's the right one to go to. How do I get there? So you can change the volume type at launch. Now, when I talk about at launch, it's not just the console. You could do it through the API. It's part of the block device mapping and CloudFormation. We've started supporting it in Beanstalk, if my memory serves me correct. So there's a lot of different places where you can say, when I'm about to launch a stack or add a new instance to my existing stack, go ahead and use GP2. It's just a block device mapping. It's already using a snapshot or a raw device to get started. Snapshots are really important in that sense because the snapshot doesn't care what type of volume you're going to. Okay? So you can go backwards and forwards, magnetic, PIOPS, GP2. It doesn't care. The snapshot will come back up again. In some cases, you might actually be able to resize your file system. So if you over-provisioned because you needed a certain number of IOPS at certain times in PIOPS, you might be able to do a file system resize in Linux to get that back down. And try and work through the sizing guide when you're getting those set up. So EBS snapshots. EBS snapshots are fundamentally more durable than Amazon EBS because they're stored in S3. We have 11 nines of durability. I don't even know how we calculate 11 nines. That's a really big, long number. 11 nines of durability is crazy. By using snapshots, you increase the durability of your data because it's now stored in S3, and at any time we can go back and use that snapshot to create the volume if there was ever a problem. So we've already replicated the data within the availability zone. We're already working very hard to make EBS extremely available. But if something did happen, a snapshot means you can bring that data back in any availability zone, and you can copy it to another region. So you can have a disaster recovery scenario where you're taking snapshots, copying them to a region somewhere else, maybe the other side of the country, another part of the world, and you can just go ahead and do create volume, bring that data back online, and you're good to go. Same way you would do it within availability zones. So I want to part a little bit of stuff around how to manage snapshots. Managing snapshots shouldn't be too hard, to be honest, because they're not actually taking up a lot of space. They're differential. I didn't really cover that in the last slide enough, but when I take a snapshot in EBS, the first snapshot, 500 gigabytes, that's 500 gigabytes. We copy it up. We definitely do a little bit of compression if we can. We stick it in S3. You change that volume by 50 gigabytes. We're only going to put 50 gigabytes up. And every time you make a change, you make another snapshot. That's what we're copying up to S3. And the EBS snapshots are smart enough to know where all the pieces are, so it doesn't matter which one of those snapshots you delete. There's always an entire snapshot sitting there that you can go back to and restore. So you're not making a full backup every time you click on snapshot. You're actually just making a differential backup. But when you're making those snapshots, it's worthwhile using tagging. I hope many other talks you've come to have sort of reinforced the value of tagging within the AWS infrastructure. But tagging means you can then go in and do a filter with the CLI and find all volumes that are marked as daily or snapshots that are marked as daily. You can look at what version they are if you're using versioning every time you take one. So they're an important concept, and I'd hope that you'd be able to start integrating those into how you manage them. So that sort of covers our introduction to EBS, the volumes, a little bit about the snapshots. Now I want to take some time to talk about the performance of EBS, how you achieve performance in EBS, what you should be expecting, and what you should be thinking about if you're not getting the performance in EBS. So I wanted to have a little bit of fun in this slide here, which is, I spoke with our EBS service team, and they were like, you want to put what up? And I was like, I'd like to start with some real fundamental stuff. Okay, so Little's law, it's a mathematical law. Unlike Moore's law, this is a real one, fully proven. Lots of people have checked it. It's there. This is fundamental to how EBS performance, the stuff I'm going to talk about, happens. Okay? So the average queue length, or the queue length, is equal to the arrival rate multiplied by the wait time. We expose these metrics in CloudWatch so you can actually sit down and work out what's happening inside EBS. We're going to talk about the number of IOPS. We're going to talk about the queue length, the queue depth. These are fundamentals that we expose to you so you can actually work out whether you're getting the performance you expect from the platform. And they're also not unique to EBS. So the EBS tuning is not being, picked up for EBS. It's picked up as a fundamental theory. So performance is typically measured within EBS as the amount of IOPS I'm achieving, how the latency is of that activity, how fast is it happening for each read and write, and what is the throughput, how much is actually being passed backwards and forwards. And I'm going to spend time talking about those so we can understand how to optimize for them or at least observe how they're performing. So to understand all of this, we need to know exactly what's going on. So we discussed earlier, it's a network-attached block store. So there's 4 components. We have the EC2 instance, the one you've chosen, and we'll get into that. We then have the I/O you're sending up and down, the reads, the writes. We have the network link, because it's network-attached block store, and the size of that link. And then we have the EBS volume itself, the type of volume we've chosen, how it's configured. So I'm going to spend time digging into 6 different areas and how they impact performance, or you can use them to improve your performance. So the first one is the Amazon EC2 instance. So there's an awful lot of EC2 instances. We launched or pre-announced C4 this morning, which is really cool. Super excited for the Haswell platform to be coming onto Amazon. Intel built us a chip. I think that's really, really cool. So when you're choosing your EC2 instance, you should be aware there's certain characteristics of that EC2 instance that are going to drive how much performance you're going to be able to get from EBS. So each EC2 instance has a certain amount of CPU, a certain amount of RAM. It also has a certain amount of network. And choosing the right size of instance means you can drive that bandwidth, that throughput to EBS. So if you grab a T2 micro instance and attach a 4,000 IOPS, provisioned IOPS volume to it, it probably won't perform the way you're expecting because they're not actually matched up. It's not designed to drive that level of performance. So once you've chosen the right EC2 instance for what you're going to be working on, you've got to make sure you've actually selected the attributes that are important on it. And so that's EBS optimized. EBS optimized is the ability to have a separate amount of network allocated to EBS so you get a consistent level of performance. If you don't do that, what you end up doing is contending the network for traffic going to EBS, traffic going to your application. It might be web requests coming in. It might be people connecting to your database. Whatever you're running on top of that, they're going to have to share the same amount of network bandwidth or the amount of network throughput that instance has. And so sometimes EBS may perform the way you're expecting, and sometimes it may not. And it's going to be really hard to work out why that is if you haven't actually allocated bandwidth to EBS and know that EBS is always going to get 500 megabytes a second or 500 megabits a second, 1,000 megabits a second. The max IOPS you can drive on an instance today is typically bound by its network, so that's our 10 gigabit instances. And on our 10 gigabit instances, we can drive over 48,000 IOPS at 16K. Now, these numbers are kind of fun. I can play with them a lot. I could make this go up to 100,000 at 4K and all these sort of things. But the thing to understand is once you understand your workload, you can drive an awful lot to EBS. The one thing you need to be aware of here is the 8 extra large, there's got to be something driving that workload. So you're probably not going to be fully saturating EBS if there's some application coming in. So you want to be balanced on that. Big takeaway here, use EBS optimized for consistent performance. If you're not doing it today, it's really easy to use it. You can go into EC2, do a stop, change the instance attribute to be EBS optimized, press start, you're now EBS optimized. You don't need to tear down your stack, you don't need to change anything. It takes about the time of a reboot to do. So it's really easy to implement. The other thing that's important when you're doing performance on EBS is understanding your workload. And so understanding your I/O size. Now, I would say that if I looked at our 2012 talk around this topic, it was really critical because 16K was where we were measuring IOPS. And so if you knew you had a 64K block size, you had to accommodate that into your design pattern. Our move to 256 has possibly made that a lot less. But it's still important to understand how many IOPS you think you're going to be sending down so you can at least have an understanding of whether the volume is delivering it or not. What kind of I/O pattern are you going to be sending to EBS? Is it going to be sequential or random? What kind of reads and writes are you going to be sending down? And then the I/O concurrency. Now, I/O concurrency has a direct correlation to things like queue length and queue depth. How much I/O you're able to have actually running against these devices. And we'll spend quite a bit of time talking about that in a second. The big change since last year, and what I really want to take away from here is that we measure up to 256 kilobyte now. Interestingly, you might find in some older Linux distributions, they're not even sending 256K down to the block device. They might have 128K set as max size. So you want to make sure you're running on latest generation instances, running on latest generation Linux distributions to really leverage all of these performance benefits. And another interesting characteristic, which is the things I've started committing to memory versus rotational speed and things like that, is EBS doesn't have a difference characteristic for read or write. So if I provision 1,000 IOPS, I'll get 1,000 read IOPS or 1,000 write IOPS or 500 read and 500 write. It's IOPS to EBS. And that's really different from traditional storage media, so it's kind of important to understand. With the change in our throughput and the change in our block size, it's now possible to be both IOP bound and throughput bound on EBS. So you can send 4,000 IOPS to an EBS volume if you're driving them at an appropriate size. And you can send 128 megabytes of throughput to an EBS volume, sequential, a lot of I/O down to a device. What you can't do is send 8,000 IOPS to a volume, even though it's not exceeding its throughput, it's exceeding its IOPS. So at that point, the volume is IOPS bound, and we need to look at larger and faster, or we need to look at striping. You also can't send anything over 128 megabytes of the volume. You'd be storage bound or throughput bound at that point. So though the volume can definitely support doing 2,000 IOPS, when you take 2,000, you multiply it by 128K, it's more than the throughput of the volume. So you're throughput bound. So it's important to understand those things. Make sure you know why your application's driving them. Is it the block size that's consuming all your throughput? Is it the number of IOPS that's consuming all the IOPS in the volume? So an important aspect of getting the performance or being aware of the performance in EBS is the queue depth or the queue length. Queue depth is the number of IOs outstanding in the pipe between your EC2 server and your EBS volume. And you want to have, if you want to drive that volume at perfect performance, a reasonable amount of queue depth in there. There is no perfect queue depth. Queue depth is a reality driven by your application and your workload, and you need to understand it and determine whether it's delivering what you expect. We'll give you some guidelines. We'll give you some insight into what we think makes sense. But at the end of the day, your application is going to drive some of these. You can observe all of these things in CloudWatch. And I have to give a shout out to CloudWatch. If you don't use CloudWatch today, you should. CloudWatch gives metrics for all of the different services within AWS. EBS is no exception. So you can go in, take a look at metrics related to your volumes, and use those to make decisions about whether the volume is performing as expected, whether you need to provision more or less. Little tip here. If you're looking at the disk IOPS and the read-write actions on the EC2 instance, you're not looking at EBS. Those are the ephemeral devices. So if you're looking at those and you can't see the traffic you're driving at your EBS volume, it's because that's not those disks. So what is I/O latency, and how do we look at it? It's the amount of time it spends going through the pipe. Okay? Now, we said it was designed for single-digit millisecond latency. So it gives you some ideas what we're trying to achieve in here. But when I say designed, that means there's definitely ways to get it wrong. I've seen latencies that go really high. So what we do is spend a little bit of time going through some graphs on random read latency. What we see here is the queue depth along the bottom, the latency in milliseconds, and then as the queue depth increases, you can see that our latency is up at 35.1. So I don't think we want to be there if we're single digits. So it looks like our queue depth needs to be all the way over at 1 if I'm looking at this graph. If I put the number of IOPS achieved on top of this, so this is a 4,000 provisioned IOPS volume we used for this testing. You can see that when we were trying to drive this volume with a queue depth of 1, we only hit about 1,800 IOPS. So even though the volume was capable of doing 4,000, we couldn't achieve it because we didn't have enough I/O driving it. And so the right way to drive this volume is probably going to be in between the 4 and the 8. I'll still be in single-digit millisecond latencies, around 2 milliseconds, and I'm going to be driving a little over 4,000 IOPS. And that little over 4,000 IOPS is because we actually have I/Os in the queue, and they're actually being worked by the system. You'll also notice that if I continue to drive my queue depth, my actual IOPS go down. I'm going to get less than I expected from the volume. And my latency is going to be over 35 milliseconds. Now, when will you see a queue depth of this length? Typically when your volume is under-provisioned, so maybe a provisioned IOPS volume, very small, you're driving a really heavy workload on that, it's not going to be able to deliver all of the IOPS you're looking for, and so it's going to start building up latency and backing up the queue, and that's when you're going to see that. So this is one of the indicators you want to take away as maybe I need to look at my volumes, and that's why we publish it in CloudWatch so you can dig into it. And just to reiterate, we don't see any differences between read and write, so it's the same graph for write as well. So an optimal queue length, I think optimal's a bit of a stretch. I think the queue length you should be looking for, the one we think you should definitely start out with, is typically between 4 and 8, around 1 queue depth per 500 IOPS. At the end of the day, you're going to have to look at your application and work out whether that's the right one or not. It might be 3, it might be 2. It really depends where you need to be. And Amazon EBS Optimized, again, offers a consistent latency experience. So if you're not using EBS Optimized and we were doing that testing in the workload, it would eat into our network bandwidth. So this slide's kind of fun. What happens if you need more? I think the quick answer from the keynote would be use larger and faster. But larger and faster is only going to take us so far, so there may be times that we still need to do RAID. And when we talk about RAID, we talk about doing RAID for increasing capacity or increasing IOPS. We rarely talk about using RAID for redundancy. Redundancy is a component or a capability of EBS itself. So if you're doing RAID 1, you're effectively halving the network pipe between EC2 and EBS. And so now you either need to over-provision your EC2 instance or accept the fact that your writes are going to be half as performant as before. And you don't really know how that's going to work. EBS is not going to come back to you and say, I guaranteed all of the EBS volumes are completely separate. So you don't have that level of comfort that you're looking for. So we're doing it behind the scenes. We make sure we've separated the volumes. But if you're creating the volumes, you don't. So it's important not to think about it from that perspective. Don't mix volume types. I have some fun people trying to do this. It doesn't make sense. All you end up with is a really weird RAID 0 mirror where one volume is like humming along and the other ones are not. What could you do if you actually striped volumes together? Well, this is some real testing we did on top of a CR1 8 extra large instance. So this is relevant to all of our 8 extra large family. We're driving 48,000 IOPS through this. You see different block sizes, number of threads. We need to have threads to be able to drive that, because if you don't have threads, you're not going to have a lot of concurrency going through it. And you can also see that we were able to drive 823 megabytes a second through that. So that's a pretty phenomenal amount of storage bandwidth in there. When you're taking snapshots in this type of system, you want to be thinking about how do you QS the file system. And there's different ways of doing it. Linux is typically a little bit more savvy in this. You do an fs freeze file system call, and that will pause the file system I/O activity for you to take a snapshot. A lot of file systems, though, are truly journalable. They're reasonably capable of recovering from consistency. So you'll be surprised how consistent snapshots are, even if you aren't able to do all of that. And when you're doing striping, if you're setting up stripe sizes on top of RAID 0, these are typically the ones we see as the most effective. So you should be looking at these. Again, it depends on your application and shooting, but you should take a look. So pre-warming. I'm not going to spend too long talking about pre-warming. Pre-warming is, because there is a first access penalty on top of the blocks, typically only ever done during benchmarking. So when people are sitting down and they're comparing volume A to volume B, they want to make sure their benchmark is representative. And so when you're doing benchmarking, pre-warming comes into a factor. For real workloads, for real production workloads, I rarely see it being required. I've yet to find a customer who could really convince me you had to sit down and do this to a volume. At the end of the day, what I'd like to leave you here with is always check our documentation. We are constantly working, innovating, changing it, because it's a service. So it's not something you get and you live with, it's a service. So check the documentation, see what the current best practices are for this, and make sure it's appropriate for the benchmarking you're going to be working on. Little takeaway if you are having to do it, the larger the block size, typically the quicker you're going to be able to do this. Especially now we have 256 kilobyte block size, it's going to go a lot quicker. So a couple of final tips I want to leave you with around performance and achieving performance in this. Typically look towards a newer file system, ext4, XFS. The two takeaways on these file systems are they're well journaled, they're well tested in the operating systems today. They're also very fast at initializing. So it's not normal that you can just attach terabytes of data to a server and expect it to be working instantly. So these file systems are helpful in bringing that forward. We have no impact today from Amazon EBS Encryption. So if you need it, turn it on. And alignment can matter. I've worked with a couple of customers on this. So you should be thinking about 4K alignment. And where I discovered this was a lot of older operating systems, the fdisk command or the make partition command, they're thinking about much older media that didn't exist or newer, they're not capable of understanding the newer media. So pay attention to that. I think my big takeaway here, if you don't need to partition, don't partition EBS. We don't expect you to partition EBS. If you need a data volume, create it, use it. Partitioning is typically required by an operating system, but for data volumes, you don't need it. We have an even bigger cheat sheet this time for the photo takers. So these are some of the numbers we think you could expect to achieve using EBS optimization on different sized instances for different database workloads. Let me just grab one out of here. So we expect that you should be able to do about 15,000 or a little over 15,000 IOPS for a MongoDB on one of our instances with 500 megabytes or megabit. And if you're up on one of our larger ones, you can do all the way up to 96,000 IOPS on those. So if we get all of this right, if we pull all of this together, we'll end up with a totally balanced system, the right EC2 instance, the right amount of EBS optimization, the right amount of EBS volumes to drive your application. So I'm not done. I'm probably going to get close on time today, but I'm not done. We have the evolution of EBS. So Werner was very kind and gave us some insight. I'm going to hopefully impart a little bit more about what's changing. So I explained basically what we have today. And we're going to have shortly larger and faster volumes. They're not new volumes. It's a service. We're able to do this by just improving EBS, and now you have access to them. That means if you go to launch a new instance, once this is available, you might be able to just dial in a bigger volume size than you were before. Don't need to re-architect. So with GP2, we're going to be delivering up to 16 terabytes of storage. Same with provisioned IOPS. You get 10,000 IOPS on GP2. You get 20,000 IOPS from provisioned IOPS. And the throughput number is 160 and 320 megabytes a second. Let me explain a little bit of how this actually is going to function for you. So a general purpose volume will always support up to 3,000 IOPS burst up to a terabyte. Now the reason for that is you always achieve your baseline performance. There's 3 IOPS per gigabyte. 1,000 gigabytes gives us the 3,000 IOPS. If I do a 2,000 gigabyte volume, my baseline is now 6,000 IOPS. The burst is there. It definitely happened. Just happens your baseline is way bigger than your burst. So you don't see it. You've got far more IOPS than the burst is going to offer. So with a GP2 volume, you're going to get the best of both worlds. Create a small volume, you're going to get tons of burst. Create a big volume, you get tons of IOPS. All of the volumes will have a maximum of 10,000 IOPS. So that means if you provision a 3.3 terabyte volume, it will go up to 10,000. If you provision a 5 terabyte volume, it will go up to 10,000, and so on. Okay? What do we think the big takeaway is here for you? Probably easier snapshots. More performance, easier snapshots. Single volume, all the IOPS and space you need. Take a snapshot when you want. Don't need to worry about QSing them. How do I build RAID arrays back up? It's a lot. Another photograph moment. So our cheat sheet gets more data and a little bit more confusing. So we now have a burst line we've added in to give you some idea of what that means for the volumes. And obviously you can see our throughput significantly increased on provisioned IOPS. 320 megabytes a second on the volume, 20,000 IOPS. I think that's pretty cool. So encryption. EBS has had encryption for a while now. EBS encryption is pretty simple. You can just do encrypt in volume. What we're going to see now is the ability to introduce AWS Key Management Service, or KMS. You're going to be able to provide a key from KMS, and EBS is going to support using that key, your key, to encrypt the volumes. So now you're in charge of the encryption keys, but you don't need to worry about the encryption itself. So the undifferentiated heavy lifting of encrypting volumes still lives with EBS, but key management, the part that's important to your CISO, the part that makes a difference when you're looking at compliance or what did I do with it, that now sits with you. You can use KMS. So what do we see are the benefits of encrypting data volumes? It protects against unauthorized access of physical volumes. For anyone who doesn't know, we do EBS encryption at the EC2 side. So that means your data is encrypted on the wire inside the AWS availability zone. And when we copy that snapshot is encrypted. Okay? So those things are really important to understand. We're not doing encryption on the EBS backend where it's only to protect the physical volume. It's the EBS volume itself that's encrypted, and so it's always encrypted when being used. We see it as significantly easy to use and reduces your operational cost if you're doing encryption today. If you're doing encryption today, you're either writing a lot of your own software, you're having to manage all of that yourself. You might be using some third-party solutions and you're having to pay an upfront cost or an additional cost per volume to encrypt. This is, here to try and save you cost and operational time. What does KMS do for EBS? What does it change in here? Well, it's going to simplify fundamentally how you deal with key management. Because it's native to our platform, EBS knows and is ready to accept the Amazon resource name of the master key or the data key you're using for the encryption without you having to sit down and install libraries or APIs or modify anything. And it's going to work with a lot more applications than just EBS. And the key management functionality it delivers are all of the things you would expect from a HSM or a key management software, and all of it's going into CloudTrail. So you can actually see what's happening with keys, who's using the keys, what volume was using a key, why was it used, when was it used. You can revoke keys. So just remember that means you're going to end up with the possibility of having volumes you can't access because you own the keys. How does it ultimately function? So it's a two-tier hierarchy in KMS, and I'm stealing a little bit of slides from our KMS team because I wanted to make sure that if you came to the EBS talk, you got some insight into how we interact with the service. A two-tiered system means that we issue a key out to the service, and the service is able to use that key to do encryption on your behalf. It's a lot more effective than having a service where every single time we need a key, we go back into the key management service. But you can also very easily revoke that key and know who was using it and when it was used. And because CloudTrail is being used, we know when the key is used inside KMS, we know when the key is being used inside EBS. So I'd like to leave with a little bit of a summary. I want you to select the right volume for your workloads. And that, for me, means GP2. Okay? Unless, of course, as we identify it's nearline cold storage or it's really high consistency databases, we think GP2 is the volume you're going to want to go with. Get the right instance for your workload. I'd love to make it that you could launch a micro instance and attach the most performant EBS volume to it, but it just doesn't work that way. So make sure when you're choosing things that the expectation you've set is matching the instances you've chosen. Take snapshots. Please, please take many, many snapshots. They're really awesome pieces of software, pieces of engineering. They're going to help you out a lot if you ever have to go back. And to be honest, the ability to copy an entire data set, all of the data you use, all the way to another region and recreate it instantaneously, it's really cool. And use encryption if you need it. It's there. It can be managed on our keys if you really don't care about key management. If you care about key management, you can use KMS, and it will work just the same. Thank you very much for coming to the talk today. It was a real pleasure. Thank you.